Hello and welcome back, everybody. Moving on to section 5.4. It's titled Eigenvalues and Eigenfunctions. Notably, this word eigenfunction will sound a little bit new. If you've had linear algebra, you're probably very used to eigenvalues and eigenvectors. So it is a true statement that most functions can be considered as vectors because they are elements of vector spaces. That just means that you can add two of them together and you can also multiply them by scalars. It's all that mathematically you need to be a vector. So yeah, a lot of functions are vectors, but when we're talking about eigenvectors that just happen to be functions, we do talk about them as eigenfunctions instead. Anyway, we're going to get through halfway through this section. First half being titled Defining Eigenvalues and Eigenfunctions. And we're really going to think about what was going on in the previous sections when we had these Green's theorems and Green's representations formula show up. The very first way we described these was as inverses, as matrix inverses, but in infinite dimensions. So I said really the Green's function was this matrix K inverse, which really isn't a matrix, it's an integral transform kernel. The K inverse, so a function of two variables for which if you acted the integral transform, forward integral transform kernel with a K against K inverse, you recovered the delta function. This really is the exact same procedure as M inverse times M, which is the same as M inverse equals the identity matrix. It's the same exact procedure as that, but in infinite dimensions or with continuous indexing, you can think. And so the point of this section is to say M inverse, wasn't the easiest thing to find. If you're taking a linear algebra course, you probably put a lot of work into finding matrix inverses, not in 2 dimensions, but maybe in 15 dimensions. It would take you a little while to construct the matrix inverse. But we actually have the following proposition that makes our life a little bit easier. If we have a matrix that we know is diagonalizable, and we manage to diagonalize it, that means that there's some transformation matrix X and X inverse, for which we put X and X inverse on either side of a diagonal matrix, where the entries in the diagonal matrix are the eigenvalues. These are all eigenvalues of M. Then we can recover M. That's the definition of diagonalization. It's using a transformation matrix X, for which when you kind of add X to the left and X inverse to the right of the diagonal matrix of eigenvalues, you recover the original matrix M. That process is known as diagonalization. If you happen to know that a matrix is diagonalizable and you have its diagonalization, which maybe isn't the easiest thing to find, but suppose that we have a matrix diagonalization, all we have to do to invert it is find the reciprocal of each of these. All we have to do to invert the matrix is find the reciprocal of each of those eigenvalues, which basically means that as long as none of them are equal to 0, they all actually have a reciprocal. You could imagine if one of them were equal to 0, the reciprocal doesn't exist. As long as all of them aren't equal to 0, then the reciprocal exists, and you can compute the matrix inverse just by finding the reciprocal. So the idea is, can we do something similar here? What would be the equivalent to some of these linear operators? Can we compute quote-unquote diagonalization of a linear operator so as to find its inverse very easily? So that's really the main question of actually the next 2 sections of the book, 5.4 and 5.5. So what does it mean to diagonalize a linear operator so as to find its inverse very easily? Well, the first thing we have to do is figure out what the heck eigenvalue means for a linear operator. So that's why we're here. Is the eigenvalue eigenfunction pair for a linear operator. So suppose we have a linear operator L, which maps a vector space to a vector space, but recall these are often function spaces, right? Functions and vectors can be thought of the same thing. So we're going to take a linear operator that's mapping a function space to itself. An eigenvalue eigenfunction pair, always associated to that original operator, is an ordered pair, lambda f in the space C, along with our function space, for which L on F is the same as lambda on F. So this really should look the exact same if you've taken a linear algebra course of mv equals lambda v is our eigenvalue equation for matrices and vectors. Now we just have the same thing, but we're replacing the vector with a function and we're replacing the matrix with an operator. Now, every time we think of operators, what you want to think about is just derivatives, like sums of derivatives, ddx plus ddx squared or something like that. These are what linear operators are, and we're just going to try to satisfy this equation. Now, independently, we can just call lambda an eigenvalue, and we can just call f an eigenfunction, but I like pairing them together. They really don't make any sense unless they're paired together into this ordered pair, which is why I will always refer to them as eigenvalue eigenfunction pairs. Sometimes you'll also see me use a subscript lambda to denote the eigenfunction of eigenvalue lambda. So that's another way of pairing them with a subscript. So I do have this remark here, which is pretty important to note, that eigenfunctions are only unique up to scaling. Like if I jump up to this equation up top here, imagine I multiply both sides by 2. Okay, there's me putting 2 on the left-hand side, but there's nothing preventing me from moving the 2 to the inside of L and lambda, and then just putting parentheses around that. And all of a sudden now I have a function called 2 times f, which is still satisfying the exact same equation. So there's nothing really special about any particular eigenfunction up to a scaling factor, right? You don't want to scale it by 0, but you can certainly scale an eigenfunction by 7, by -4, by 2,478 if you wanted to. But whichever one you find first is more than enough for anybody to be happy that you found one. And in some situations, if you have something called a norm of the space, it's quite common to normalize the eigenfunction. But if you don't have a norm on the space, that's also kind of a topic for another course. If you don't have a norm, then you don't really worry about normalizing it. Anyway, let's look at some examples of these eigenvalue eigenfunction pairs. So let's just start out with the derivative. Now, every time I ask questions about eigenvalue eigenvector pairs, I do talk about kind of the vector spaces themselves, right? So we do care a lot about these vector spaces themselves that the linear operator is acting over. In this case, we're going to give ourselves a vector space C infinity R. And if you've forgotten how this is defined, even though I did define it way back in chapter 1, these are just functions whose domains are R and maybe their codomains are C, and all of their derivatives exist. That's what it means to be C infinity. That means you can take as many derivatives as you want. Now we can look at the derivative operator ddx as a map between this space and itself, right? So to be valid for eigenvector or eigenvalue eigenfunction pairing, you need to map a space to itself. So thankfully the derivative maps the space to itself. You know, if a function has infinitely many derivatives, then certainly after I take one derivative of it, it still has infinitely many derivatives. So this is a good example of a space that the derivative operator maps into itself. We can actually find eigenvalue eigenfunction pairs of the form lambda e to the x, and that's just because, hey, all I need to do to verify this is grab my eigenfunction, or what I claim to be an eigenfunction, and plug it in, actually compute the derivative on there. What do you know? The chain rule says I get lambda times e to the lambda x. So all I've done is I've replaced the derivative with multiplication. It's a definition of an eigenvalue eigenvector pair. This is actually going to be true for any lambda in the complex numbers. Because of the way my space was defined, I didn't really have to restrict lambda to anything special here. So that's just a nice example with the derivative. Here's an example for the derivative. The definition of a different vector space, C infinity, on the torus. Now this symbol, maybe you forgot it. That's the one-dimensional torus, also known as the unit circle. Circle not being the disk, just the boundary of the disk. So it's the one torus or the unit circle, or -pi to pi endowed with periodicity. Periodicity meaning that I'm allowing -pi and +pi to be understood to be the exact same point, which everybody knows that's how the unit circle behaves. -pi and +pi are the same point. So what is this space? It's just the space where all derivatives exist. That's the infinity part. But because we're endowed with periodicity on -pi and pi, what we need that the limit as x goes to -pi of all of our derivatives to be the same as the limit as x goes to pi of all of our derivatives. So this is the space C infinity of the one torus. And the derivative operator on here admits the eigenvalue eigenfunction pairs. Well, now it's changed, right? So up top, in the previous case, I gave lambda e to the lambda x. I'm being a little bit more restrictive here. I'm saying now the eigenvalue eigenfunction pairs are ik e to the ikx. Now, of course, that looks very similar, but this is now only true for every k in the integers, z. So we don't recover, for example, even just 1 e to the x is not an eigenvalue eigenfunction pair. Why isn't 1 e to the x an eigenvalue eigenfunction pair? Because certainly we still have this property e to the x is e to the x. There's a 1 here. Why isn't that a valid property? Well, it's because e to the x is not in this space. If I tried to look at the space, if I try to take the limit as x goes to -pi of e to the x, I just get e to the -pi. If I try to take the limit as x goes to +pi of e to the x, I get e to the +pi. Because e to the -pi and e to the +pi are not the same thing, these are not going to be equal to one another, and I'm not in this space. So I have to be very, very particular about making sure that whatever shows up in my eigenvalue eigenfunction pairs actually is an element of the space, or as far as the eigenfunction is concerned, is actually inside the space I'm concerned with. You can see that the way I guarantee that my eigenfunction e to the ikx is actually in there is that you can go ahead and compute the limit of all the nth derivatives of basically our original eigenfunctions, but then now we're requiring that e to the minus lambda pi and e to the lambda pi are the same number. That can only occur when lambda is ik for a k in the integers. And this goes back, basically, that looks like your Fourier. These are kind of your Fourier basis, right? So I have this remark now because of those last two cases, and it's something that I would often forget when I was a student. That's that the collection of all eigenvalue-eigenfunction pairs depends intimately on the domain of the operator. So you have to pay extremely close attention to the domain of the operator. Sometimes it's going to be hiding in the problem. Like imagine if maybe I hadn't written this in the problem and somebody just gave it to you like this. The domain of the operator is hiding in here, but you have to pay attention to that. I cannot stress it enough that the domain of the operator is just as important as the operator itself when it comes to eigenvalue-eigenfunction pairings. So that domain plays a huge role because in the top case, that's C infinity of R. In the bottom case, that domain, it's hiding right here, right? C infinity of T1. And all of a sudden, the entire collection of pairings becomes different when you change that domain. So you have to be really careful about that. And I kind of just add on to what I said verbally about the last two cases here where I give some color choices to try to emphasize where those domains show up. Anyway, that's always very important. This will show up when we're actually solving the problems as boundary values, okay, or initial conditions or some other condition on the problem. But basically in the first case, you really just had the condition on your differential equation that the nth derivative exists, where in the second problem you actually have the boundary conditions of the differential equation, where the nth derivative at negative pi is equal to the nth derivative at pi. So this is a boundary condition in ODE from the torus. Right? When I included the torus, you actually gained a boundary condition. So there's going to be conditions that the domains of our operators place on our eigenvalue equations, and it's going to be really important that we keep that in mind when we start looking for those. Anyway, we do have a name for kind of the collection of all eigenvalues of an operator. In linear algebra, we gave it the name the spectrum. The collection of all eigenvalues of a matrix is called the spectrum. This is where we get the word spectral theory from in the spectral methods. It's called the spectrum, but when we get to operators, we actually have to give the spectrum an extra name here. It's the name point spectrum. Because it turns out there's some other versions of spectrums for linear operators in infinite dimensions that they don't necessarily have to look like eigenvalues. So we're going to work with the point spectrum of an operator by thinking about the collection of all lambda for which the eigenvalue equation is satisfied. And of course, there's the f and v. That's where the domain plays a really important role. So you've got the point spectrum denoted by sigma sub p of an operator L. It's just the collection of all possible eigenvalues. This will play a role in section 5.5 to us. Now let's look at our previous two examples and compute their point spectra. If I take my derivative operator on and basically place no restriction on the boundary of that derivative operator, then the point spectrum is the entire complex numbers because I already know that I can satisfy the eigenvalue equation for any lambda in the complex numbers. On the other hand, if I restrict my domain to smooth functions on the torus, so they have to be periodic now, then actually the point spectrum of this derivative has shifted from the complex numbers. Now it shifts just to I times the integers, right? Which is of course the set ik when k is in the integers. So I get vastly different point spectra. For the same, and I'll put that in quotes, same operator with different domains. This does play a very important role in section 5.5 and actually in the rest of PDEs, but we won't tend to get to there in this course. But this idea of domains of operators will play a role in all sorts of PDEs problems. We're just going to finish then today with just a collection of other operators and their eigenvalue eigenfunction pairs, just because these are some common ones that we're just going to get a little bit used to. And so this first example is the Legendre polynomials, where here's my operator. So we're looking for L for operator. My operator is over here. It's a derivative and then a multiplication by x squared minus 1 and then another derivative. So that is my operator that I'm going to do. It's really a collection of three operators, right? Because that's considered as multiplication by x squared minus 1. And so it's really just the composition of three linear operators. And this actually has a collection of eigenvalue eigenfunction pairs. The eigenvalues look like n times n plus 1 for n in the natural numbers, including 0. And the eigenfunctions look like this thing called p sub n. It's given the name p sub np for polynomial here. And it turns out this p sub n is just defined as this lovely collection of a coefficient times the nth derivative of x squared minus 1 to the nth power. So those are known as the Legendre polynomials. I'm really just giving you a nice example here, which means that the point spectrum can be found by looking at all possible combinations of n times n plus 1, which by the way looks like 0, 2, 6, and 20, and so on. So it's just like a nice little discrete point spectrum there for you. But probably some of you weren't even thinking about this so far. It's actually the most important thing we've talked about. Really tried to emphasize this. Nobody asked the question. Obviously, nobody's here talking to me. I'm all by myself in a room. But nobody asked the question, what's the domain of this operator? That plays a really important role. What is the domain? We better look at it. The domain is functions defined on the interval -1 to 1 into R, such that the left-hand and right-hand limits exist. Because it turns out there's something known as the Legendre functions of second kind, where these limits do not exist. Okay, so this is where things all of a sudden will change depending on whether or not you're placing some restrictions on the domain. What I've done here is provided some nice examples for you. This is what it would happen if you calculated the first 5 of these out, and we've got a picture there for you showing all of them. Another good example is the Bessel functions of the first kind, and I put those in parentheses as well. These have some pairings between an alpha squared and j sub alpha, for any alpha in the natural numbers as well. Once again, these can actually extend out of the natural numbers, but once again, it just kind of depends on what is the domain of the functions I care about. When the domain is just that the first derivative exists everywhere in the complex sense, this is what forces us to have alpha in the natural numbers. This is a perfectly well-defined summation if alpha is in other numbers, but we don't gain that the first derivative exists everywhere in the complex sense. So there's a lot of niche aspects going on with the way that this domain plays a role in the collection of eigenvalue, eigenfunction pairs that are admissible. Now we will actually see where these terms come from in the next video, but for now with both the Legendre and Bessel functions, I just want to introduce them and say, look, these things exist for some other complicated operators. In fact, the Bessel operator is x squared, 2 derivatives in x, plus x times 1 derivative in x plus x squared by itself. So it's just, you just define a specific operator, and then you have a class of eigenvalues associated to eigenfunctions for a specific set of eigenvalues. And so you can find the point spectrum here, which is all squared natural numbers, including 0. So you get 0, 1, 4, 9, and so on. These are the eigenvalues of the Bessel operator. I can show these on a picture as well. They look like the following. They actually are pretty darn important when it gets to some Laplace equations, because these are, if you rotate them cylindrically, right, you can kind of imagine this as like a nice cylindrical wave-looking thing. These actually describe waves in a drumhead, a circular drumhead. And you can find that by calculating the eigenvalues of the Laplace equation. And so that's where these tend to show up in people's initial experience with them, but they do show up in a lot of other situations as well. But that's just a nice second example of some of these cases of eigenfunctions with respect to a specific operator. And then let's actually jump to maybe a partial differential operator that everybody here knows and loves. I'm going to give it a negative sign just for fun. So I'll say the negative Laplacian, and now everybody's keenly aware that I do have to specify my domain from the beginning. So I've got the negative Laplacian, but it's defined on the domain C infinity sub 0 of the square 0 to pi squared. Now what is this? A little typo here, 0 to pi. It's functions from 0 to pi squared into R, for which the gradient exists for all k. That's what the infinity means. And then in particular, what does the sub-0 mean? This means that the limit at the boundary equals 0. Or in other words, the boundary value is 0. So on the entire square boundary of the square 0 to pi squared, I need a boundary value of 0. That's what the sub-0 in my C means. And so we're asking questions about this operator, negative Laplacian, specifically on smooth functions which are 0 on the boundary. And what we can do with that is set up a PDE which reflects this. The eigenvalue equation is just negative delta phi equals lambda phi, and then this would be like for x and y in the entire square, 0 to pi squared, and then we need phi to be 0 on the boundary. And so you gain these boundary conditions just because of the definition of the domain of the operator. And then if you were to go ahead and solve that eigenvalue PDE, you find out that your pairs, your eigenvalue, eigenfunction pairs, look like lambda squared plus mu squared, and then sine of lambda x plus sine of mu y, where both lambda and mu are allowed to be in the integers except for 0, because of course plugging in 0 here would make the entire term 0, and nobody likes that. So you can choose whatever else you want, and we can plot some nice examples here for lambda being 1, mu being 1, that's this equation, lambda being 2, mu being 1 is this equation, lambda being 1, mu being 2 is this equation, and finally both of them being 2 is the bottom right. But you could continue for infinitely many of these and plot them out, and you just see the eigenvalues of the Laplacian. Now in this case, this would be, these are the shape of waves on a square drumhead. Not that square drumheads are very common, but you could imagine if you did have a square drumhead and you hit it with a stick, the waves actually do look like this, or even a trampoline if you want to think about it that way. That kind of makes sense, right? The boundary is going to be fixed, but the rest of the sheet's going to vibrate a little bit. In particular, what modes does it vibrate in? This is what it would look like. Anyway, in the next video, we're actually going to talk about calculating these. For now, I just wanted to provide some examples and kind of the motivation for why we're going to study eigenvalues of operators. I'll see you then. Bye.